I've switched it on. Okay, good afternoon, everyone. Good afternoon. Good afternoon. Good afternoon. So last class, we looked at the following. This is a very brief recap. I did not want to start writing once lecture begins and waste time with that. This is all available from last class. Okay, I just want to go over it very briefly. All right. Thank you. So we start off with an RC circuit. Okay, and this is the simplest of the circuits from that perspective. The input voltage is a source voltage Vs of t. The output is a harmonic output because the input is also harmonic. Okay, and so we have Vs as a sine omega t. Vc, after doing a lot of things, we figured out it can be written in terms of the magnitude of the transfer function and also this phase term phi, which is given as the angle of the transfer function. Okay, and we also were able to come up with a transfer function for the system, which is T of S written right here. The tau is a time constant. It's R times C, resistance times capacitance. Important point takeaway is this quantity here. This is your frequency response function. Okay, this is the quantity that we will always be looking for when you perform frequency analysis. Okay. And another point I want to make here is that this terminology here, this is called as the total system gain. The total system gain is the ratio of the output to the input, magnitude of that, and that is essentially the magnitude of the frequency response function. So in the homework or in the exam, I'll tell you, okay, here is a circuit, obtain its frequency response function. What do you have to do? You have to use a method of impedances, and we're going to solve some problems, of course. You'll use a method of impedances. You'll come up with a transfer function of the system relating the output and the input. You convert it into the Fourier domain. Essentially, we are doing a Fourier transform here by converting S is equal to j omega. Once you do that, you get your frequency response function. Okay? So this is the key to all of our calculations. Then we said, okay, what is our purpose here is to understand how the system response varies as a function of the input frequency. Okay? And a good way of visualizing that graphically is by using the Bode plot. In the Bode plot, we define this term called as the gain term. People call it the gain. I just like to call it as the magnitude m, okay, or the amplitude. The amplitude is 10 log 10 of this input and output power ratio, which is measured in decibels. Okay, so all of these are measured in decibels. And one can write that in terms of the magnitude of the transfer function, which we wrote down in the last class. Then we can perform an asymptotic analysis. For very low values of the frequency omega, we get the gain to be, or the magnitude to be 0 decibels. For very large values, you get a quantity that is decreasing 20 decibels every decade. Okay, and we sketched it as well. So this is 0. This was the low frequency asymptote, high frequency asymptote. They intersect, these two, at omega is equal to 1 by tau. And at omega is equal to 1 by tau, if you go ahead and calculate the magnitude m, you will end up getting it to be actually minus 3 decibels. Okay, so m here at omega is equal to 1 by tau, minus 3.04 or minus 3 decibels, okay, approximately. And this is called as the cutoff or the corner frequency or the break frequency of the system. And we decided why it was called this way is because when omega is 1 by tau, the output power is half the input power. All of these details we took care of in the last class. I want to see if there are any questions that I can help take care of here. And the actual Bode plot itself will look somewhat, not as much of a straight line, but as a curve. And this value here will be at the corner frequency. Okay? Okay, I want to see if there are any questions before I proceed with today's class. Our aim typically is mostly to look at the magnitude plot, but just for the sake of completion, I also want to do the phase plot for this particular problem. It's a simple problem, it won't take too much time. Perhaps you've seen this as well before. So the phase plot, and please note this is not something that I will be bothering with when we do higher order frequency response analysis. Okay? So for the phase plot, here is what we do. We plot the phase in radians versus the system input frequency or the carrier frequency in radians per second, all on a log-to-log scale. Phase of the system is the angle of the transfer function, or it's called the phasor, right, essentially. So combined with the magnitude, it's called the phasor. So this is T of j omega, and we have that written as minus tan inverse omega tau, or I will write this as tan inverse of minus omega tau. Okay, no harm done. We once again do the asymptotic analysis. We say, okay, what happens to the phase at very low values of omega, at very high values of omega? What happens? How do you match them together, which is an interesting situation here. So for omega much less than 1, I'm going to call it as phi low, is minus tan inverse of omega tau, but omega is very, very small, right? So this is approximately 0 degrees, okay, because omega is very, very small. Sometimes people also call this to be as pi radians or pi 180 degrees, but I will stick with 0 because it is convention typically to start from 0 for a low pass filter. So this is 0 degrees or 0 radians. Then we have the high frequency asymptote, omega much greater than 1, so phi high is minus tan inverse omega tau. Omega is very, very large, which means that the quantity inside is essentially infinitely large. Okay, so if you look at it that way, it's an asymptotic analysis. Tan inverse of infinity is 90 degrees, pi by 2 radians. So this is minus pi by 2 radians. I will also calculate one more value at the corner frequency. Okay, so at omega is equal to 1 by tau, the value of phi is the following. So phi at 1 by tau is minus tan inverse of 1 by tau times tau, which is minus tan inverse of 1. Tan inverse of 1 is 45 degrees, so this is minus pi by 4. So many radians. Then we plot. This is omega, log scale, potential minus 2, minus 1, 0, etc., etc. On the y-axis, we have phi directly read as radians. And if you have confusions on the log scale versus the linear scale and so on, please look back at the previous lectures notes which were posted on Carmen. I have some very simple and silly examples which are kind of enlightening as well. Okay, so 0 degrees or 0 radians minus pi by 4 minus pi by 2. I plot the low frequency asymptote, so that's just a flat line going through 0. I shouldn't probably be stretching it all the way along because it's supposed to be a low frequency asymptote, but bear with me. Then I'm going to have the high frequency asymptote, which is minus pi by 2 at all times. And interestingly, they don't meet. Like two parallel lines intersect at infinity, if you believe in infinity. We don't, as engineers, believe in infinity, so what do? We come up with a quick fix. This is just completely arbitrary, but people have been doing this for quite a while. Okay? Completely arbitrary. You look at omega is equal to 1 by tau. Okay, so let me get rid of this scale here, so you know what it means. Let's say omega is 1 by tau is somewhere here. Then you look at 1 decade before this, 1 decade after this. Okay, so 1 decade before this is omega is 0.1 by tau. And 1 decade after this, omega is equal to 1 by tau, the corner frequency is 10 by tau. 10 times. Then you draw a vertical line from the lower end of the spectrum, omega is equal to 0.1 by tau, intersected all the way to the low frequency asymptote. Then you do the same thing, you take the higher end of the spectrum, which is 10 by tau, intersect that with the high frequency asymptote. Then somewhere in between, at omega is equal to 1 by tau, I know that the value is pi by 4 with a negative sign, so we have taken care of that. And then you join all of these points by a nice smooth straight line. Okay? And so the phase plot is now going to look as the following. So it's going to start off here. and then it's going to fall down by 45 degree or whatever is the angle there, right? And then it's going to go off into the high frequency asymptotes. And this is done so as to purely understand it from a mathematical perspective, okay? Because the high frequency and the low frequency asymptotes are approximations. If I take the actual phase and calculate values of omega and then plot the figure, it's not a discontinuous plot. It's a nice, smooth, continuous plot. So if I look at the actual plot itself, so that dotted line there would be the actual phase plot. We want to get to the actual phase plot somehow by an arbitrary yardstick, and this is exactly what we're doing. Okay? This does not hold any glamour or appeal for me as a mechanical engineer, so we're not going to focus much on the phase plot. We will focus more on the magnitude plots. I want to see if there are any questions on the phase plot. I just want to close the loop here. Okay? Idea is very simple, asymptotic analysis, and we will solve quite a few more problems in the next class and then in succeeding classes so that this becomes second nature. Okay, I'm going to move on to second order frequency response, which is more challenging. Let's start with a simple example. Okay, the simplest example of a second order circuit is an LCR circuit or an RCL circuit. Okay, so second order response. In the frequency domain. I'm not going to do the body plots today because we have enough to talk about in terms of the second order response. We will come across the terms called the resonant frequency, and then we will also look at the system peak values, and eventually we will define a factor called as a quality factor. Okay? The three things that we will do. Alright, so here I have an RCL circuit. This is Vs source, sinusoidal source. That's why we are doing frequency response analysis here. Then I have VR of T, resistor R, then the capacitor C. Vc of T. And then I have an inductor element, which, as you know, stores energy in its magnetic field based on Ampere's law and Faraday's law combined together. And this is VL. And somewhere at some node I have a ground reference. I want to come up with a system model that relates Vs and Vc. Okay, so model relate Vs. This is the system input and output. You can take the output anywhere. I am interested in Vc because it gives me a nice looking equation. And Vs of T is A sin omega T. Okay, we use the method of impedances, right? We replace each of these by an impedance block that measures the impedance or the resistance of the current flowing through that particular element. So replaced by impedances. Impedance of the resistor is capital R. Impedance of the capacitor is 1 by Cs. C capital R capital. Okay. Now people in the back, can you see my writing? Okay. And then this is Ls. And we are now in the frequency domain because you're doing a impedance analysis. So this is Vc of S, Vr of S, Vl of S, and then I have the source voltage, which is Vs of S. Kirchhoff's voltage law. The potential drop across the passive elements, the sum of all those potential drops is equal to the potential rise across the source element. Excuse me. There's only one source element here, so Vs of S is Vc, Vr. This is by KVL. You could have done it in the time domain, no harm done, and then take the Laplace transform. That's also completely fine. This is easier. Current flowing through, the direction of the current, depending on what I put as a positive and a negative signs. So this is a clockwise current. I'm going to say this I of t, so it becomes I of S. And it should be very obvious that it is the same current flowing through all the three impedance blocks, which means that they are in series connection. And if impedance blocks are in series, I can replace them by an equivalent impedance, which is just the sum of the individual impedances. Okay? So I just do that. I of S, so R, Ls, 1 by Cs in series. And so obviously Z equivalent is the sum of all of these. R, Ls, 1 by C times S. Common denominator takes Cs, multiply throughout, I get the following, starting from the largest to the smallest order. So I have the equivalent impedance, great news, nothing surprising there. What's my output? My output is Vc. So I write the relationship between the voltage across the capacitor and the current flowing through it in terms of its impedance. Okay, so I have Vc of S, by I of S is the impedance of the capacitance, capacitor element, so that's 1 by Cs. And once again, if you have things in series, the voltages add up, which is why the voltage drop across the equivalent impedance is Vs of S. It's the sum of Vc, Vr, and Vl. Okay? We looked at this when we did the RC circuit last time. So without much calculations, we can say the following. Vs by I, right? This is the transfer function across the equivalent impedance block, and so this is just going to be the following, right? LCS square plus RCS plus 1 by C times S. This is Vs of S by I of S. I'm going to do the following. I don't care much for that I of S creature. So I'm going to look at that ratio there because I have to bring the voltage drop across the capacitor into play. I cross multiply, and Vc times Cs is equal to I of S. Okay, so I replace it as does this make sense to everybody? I'm just cross multiplying stuff, nothing earth shattering. And if I now write these two expressions next to each other, which you don't need to, you already have them. Is Vs times that Cs is a common factor, cancel it off. Cross multiply, I need Vc and Vs relationship. LCS square is Vs of S. Okay. Normally I would stop here and then look at the frequency response function, but I want to do a few more things. So here is what I'm going to do. I'm going to take this expression, invert it, bring it back to the time domain. Okay? So I'm going to rewrite it for our benefit. So LCS square or CS Vc of S is Vs of S. Invert it back. If you invert it, if you see an S square, then whatever was the term that is attached to it in terms of the output, that becomes a second derivative. Right? We've done this multiple times, so I'm going to skip the details. So invert. I get LC Vc double dot of t. Now I'm going back into the time domain. Then Rc Vc dot of t. Plus Vc is that, and this is obviously the system model in the time domain. So if I ask you for the system model, this is exactly what you have to do. Use the impedance method or use any method of your choice, I don't care. Come up with the time domain specification of the system in the form of an ordinary differential equation. Okay? Okay. I still don't like this. It's not in the standard form. So which means I write what the standard form is first. And again, this is the standard form, not the form that you like. Okay? This is the standard form of a second order ordinary differential equation. Does not really matter what happens here. F of t could be 1 by m times f of t, 1 by k times f of t. Does not really matter. That is just a function of time. I am interested mostly on the left hand side of the equation. So this is the standard form. obviously our system is not in the standard form, right? Which means that I have to divide through by LC. So I divide through by LC. And then I get the system in the standard form. If I look at it, this is now 1 VC double dot plus RC divided by LC. This is supposed to be a C, in case there was any doubt. RC divided by LC is R divided by L. So plus R by L VC dot VC by LC is and now we are talking. I have the standard form, I have my system model written in the standard form, some garbage on the right hand side, I don't care. I'm looking at the left hand side. If I look at the left hand side, then it automatically says that what is omega n square? Omega n square is 1 by LC. So omega n is square root of 1 by LC. Okay, so omega n is square root of 1 by LC. Need to calculate zeta, which is slightly more tricky. So here is what I'm going to write. I'm first going to write 2 zeta omega n is equal to R times R divided by L. Okay, so 2 zeta omega n is R by L. I'm going to give a brief pause here if you want to catch up. And I'm going to work with those two to obtain zeta. Okay. Okay, just for my own thinking, because I forget what I write, so I'll rewrite it again. VC double dot R by L VC dot Vs of t, and then we had omega n square as 1 by LC, or omega n square root of 1 by LC. 2 zeta omega n is R by L. I can solve for zeta. Okay, I'm not going to go through the steps, but this is what you end up getting as zeta. So zeta is R by 2 square root of C by L. And if you are really picky, an interesting exercise is to substitute for all the units of R, C and L. L is in Henry, C is in farads, R is in ohms. Bring it back to the basic units. And then you will figure out that zeta does not have any units, it's dimensions. Okay, and obviously you'll end up getting this to be as 1 by seconds frequency. Okay, so that's great, but this is still not what I want to do. But I want to write these things down, and I want to point out one more thing. Two zeta by omega n, just randomly writing this down, is 2 R by 2 C by L. 1 by omega n is square root of C times L. Square root of L cancels off 2 and 2 cancel off. C square root multiplied gives me RC. Okay, this is the third thing I want to write. And I want to see if there are any questions so far. what did we do? We took an RLC circuit, it's in series connection. We came up with the system transfer function, which kind of got buried in the details, but I'm going to unpack it again. Then I worked my way backwards and said, okay, this is no good for me. I want to obtain the natural frequency, I want to obtain the damping ratio. Okay, those are the two system parameters. That tells me everything I need to know about a second order system. Great news. This is just something that will be very useful in a second. Okay, the RC term. Now, I want to go back to the frequency response function that we had earlier. Okay, so the system transfer function is Vc by Vs, and if you take the Laplace transform on both sides, and we already did this, so I'm not going to go over it again. So this gives me 1 by LC S square RCS plus 1. We had already obtained this. Okay, I took a detour just to calculate omega n and this zeta picture. Now, take a look at the transfer function. But I'm going to write it in the following manner. I have LC times S square, so I'm going to say this is S square by 1 by LC. Plus RCS plus 1. What's 1 by LC? Omega n square, not just omega square. Okay, omega n square. So this is 1 by S square by omega n square, the natural frequency of the system. Every system has a natural frequency, not just a mechanical system. An electrical system can have one, a fluid system can have one. Thermal systems do not have a natural frequency, they have only a time constant. S square by omega n square. What's RC? Our good old friend 2 zeta by omega n, which is what I had just written there. So this is 2 zeta omega n S plus 1. So now I have everything written in terms of the system parameters. Okay? And it is at this juncture that I take the frequency response function by substituting S is equal to j omega. So T, when S is equal to j omega, substitute, it's 1. I have an S square, so j omega whole square or minus omega square. Okay, so this is j omega whole square by omega n square 2 zeta by omega n times j omega, and then this measly 1. J square is minus 1, which means that this is no longer an imaginary number, this is a real number. Okay? So I'm going to take this quantity, which is now a real number, attach it to the 1 here, and now I have a complex number. You'll see. So this is now 1 minus omega square by omega n square. Once again, what did I do? I wrote the transfer function down. After I wrote the transfer function, what else did I do? I started writing this in this crazy form here because I recognize this is omega n square. And I also recognize that R times C, with a lot of foresight, is 2 zeta divided by omega n, which we will be using later on. Okay? Then I find the frequency response function, which is substituting S is equal to j omega. As a j omega whole square, so j square is minus 1, and 2 zeta omega by omega n with the j next to it. This is a complex number. right? The numerator is a complex number as well, because it is 1 plus j times 0. The denominator is also a complex number. Okay? Now we make a substitution. We say, okay, it is too much trouble to write this omega by omega n all the bloody time. And so I'm going to say, hey, let me call omega by omega n as a character little r, which is going to be called as the frequency ratio. Okay, so say little r is omega by omega n. This is a frequency ratio, r for ratio. If I do the substitution, then my frequency response function, which is t of j omega, is now 1. Wherever I see omega by omega n, replace it with an r. I have an omega square by omega n square, so that's r square. Two zeta omega by omega n, that's an r. And you've done this in time domain analysis, because you'll say, okay, hey, zeta could be greater than what? Critically damped. I'll be getting real and distinct roots. I could have zeta equal to 1. I'm sorry, overdamped, zeta greater than 1. Zeta is equal to 1 is critically damped. Not interested in these two. I'm interested more in the case when zeta is less than 1. We are not there yet. We still have some more things to do here. Okay? This is the frequency response function. For a second order system, you always write it in terms of this frequency ratio r. Why? Because it's easier to write r rather than omega by omega. That's all. And it's convention. People have been doing it for 200 years. There's no reason for you to change. What are we interested in? As we said, magnitude. Not in the body plot yet. This is just simple plain magnitude of a complex number. The magnitude of the numerator by the denominator. So if I look at the magnitude, this is the square root of the sum of the squares of the real and the imaginary parts. So this is 1 square root. The real part square and the imaginary part square. Okay, what's the real part? The real part is 1 minus r, so square of that. And the imaginary part. When you have the magnitude, you're always interested, okay, what's the maximum value? Right? So how do I find the maximum value of this quantity here? Any thoughts? So I have this expression here. How do I find its maximum value? I could start plugging in r is equal to 0 and go all the way to infinity. We have better things to do. Yes?
We can minimize the denominator.
You could minimize the expression, the whole function, right? Because it's a function of r. So I just have to differentiate with respect to r. So to obtain the value of r at which is a maximum, we do d by dr of that term is equal to 0. Obviously, I'm not going to sit here and do differentiation. I'm just going to write the expression. So d by dr of 1 1 minus r square whole square 2 zeta r whole square is equal to 0. So if I differentiate that, I'm going to get the value of r. I'm going to go past this really quickly. So this is the differentiated result. Okay, so some random stuff, and then the stuff that's more important is the differentiation of the terms that contain r within 1 minus r square whole square and so on. So that gives me 2 1 minus r square. Differentiation of r square is minus 2r. Differentiation of 2 zeta r whole square is 4 zeta square times that's equal to 0. You see a factor of 2r, right? That's constant for both these things. I have a negative sign. This entire garbage goes off because it's going to be cross multiplied with respect to 0, so I'm not having to do anything with the square roots and 3 by 2s and so on and so forth. So all I'm left with is a very nice expression which is sitting inside here. And I'm going to unpack that. I'm going to get rid of this panel right here. Okay? So I end up with 2 times 1 minus r square with a negative 1 plus 4 zeta square is equal to 0. So factor of 2, there is a 4, so this becomes 2. Negative sign, bring it onto the other side, so I have 1 minus r square is 2 zeta square, or r square is 1 minus 2 zeta square. Which implies r, now I'm going to call it by a special name, which is now the ratio of omega capital R. Sometimes that's also called as omega little r, okay, makes no difference, by omega n. This is square root of 1 minus 2 zeta square, or omega r is omega n and you should know the name of this from your electrical systems class. This is called the, or perhaps not, okay, so this is called the resonant frequency. Okay, so this is not covered in your circuits class. Great news. So maybe I should have gone a little slower. Hindsight is 20/20. Okay, this has great import for us because resonant frequency, and you're going to see this in a second, okay, this is the frequency at which the magnitude of the response is the largest, right? So it is possible perhaps that if there is a foolish designer, that person will say, okay, hey, get rid of damping. Damping is screwing me. So, if I get rid of damping, and then I go ahead and calculate the peak value of the frequency response function, it's going to blow up, it's going to give me infinity at the resonant frequency. And you're going to see this, okay? I'm going to wait until everybody has all the details down here, and I'm going to pull the top panel down. I have a couple more things to do before we quit today. And this is a lot to take in, and I understand that, but there are some common things, right? You have a series circuit, use impedance methods, combine them into single effective impedance. You take the Laplace transform on both sides, you get the system transfer function, frequency response function. We had to do some mental gymnastics to bring it to this particular form and then write it this way because it is easier to deal with these creatures then. Okay? So here is the story so far. The story is this guy is 1 minus r square whole square zeta r whole square. Okay, this is the magnitude of the frequency response function. When omega is equal to omega r, which is omega n square root of 1 minus 2 zeta square, the magnitude of the frequency response function becomes a maximum. I want to calculate that maximum value. How do I do that? Is just by substituting omega is equal to 1 minus 2 zeta square root times omega n. Okay? So substitute, so to obtain T peak or T suffix p, which is the maximum we substitute